welcome you all in the lecture series of Detailed Electronics KV 039/049. Myself Dr. Kishanu Kundu, and we are discussing about the combination circuits, and in this lecture we will be focusing on multiplex display, serial and parallel adder. Okay. So, let us begin. These are the table of content for today's lecture. We are going to discuss 7 segment display, BCD to 7 segment display, decoder circuit. We will be discussing about parallel adder and we will be discussing about serial adder. Okay. So, let us begin. So, first of all we will be going to discuss about 7 segment display. 7 segment display already you have seen in traffic lights, right. So, that thing how it works, what is the logic behind this, we are going to study here. So, 7 segment display actually consists of 7 LEDs, okay. That is why it is named arranged in rectangular form. Each of 7 LEDs is called a segment, because when illuminated the segment forms a part of numerical digit to be displayed. An additional 8th LED is sometimes used within the same package, thus allowing the indication of a decimal point also DP when 2 or more 7 segment displays are connected together to display numbers greater than 10. So, one display can display up to 9 itself, 0 to 9. Okay. If greater than 10, then we have to take 2 displays, right. The display's common pin is generally used to identify which type of segment display we are using. Actually 2 types are there, common cathode, common anode. So, as each LED having 2 connection pins, one called the anode and another called the cathode. So, the 2 types, one is common cathode and second one is common anode. So, let us check the picture of LEDs. So, you can say there are 7 segments, right, A, B, C, D, E, F, G. A, X, one second, A, B, C, D, E, F, G, total 7 segments are there. So, now for displaying 0, which will be active? See, A is active, B will be glowing, C will be glowing, D will be glowing, E will be glowing and F will be glowing, right. To this is nothing but numeric 0, this is 0. To display 1, only B and C will be active, will be glowing, right. To display 2, will be having A, B, D, E and G as active, right. Like that for displaying 3, A, B, C, D and G will be active. For 4, we will be having B, C, G and F. These combinations, you have to remember these combinations very carefully, because when we are going to write the truth table, this logic is very needed. Okay. So, now this is 5. For 5, we are having A, C, D, F and G as active. For 6, we are having A, C, D, E, F and G. For 7, we are having A, B and C, very important. Number 7, very important. For 8, we are having A, B, C, D, E, F, G, all are active. For 8, all are active, and for 0, all are active except G. Okay. And for 9, we are having A, B, C, D, G and F are active, right. So, whatever I have told so far, we are going to check in the display, right. So, for displaying we are having this, you can check A, if we write a truth table. So, A, B, C, D, E, F and G, if we write like this. Okay. So, for 0, to display 0, we will be having A is 1, B is 1, C is 1, D is 1, E will be 1, F will be 1, only G will be 0, right. Again for 7, if I going to write 7, so for 7 A, B and C will be 1, A, B and C will be 1, rest will be 0, right. Like that for 9, or you can take 5, we can take 5 for displaying 5, we are having A is equal to 1, B is equal to 0, C is equal to 1, D is equal to 1, E is equal to 0, F is equal to 1 and G is equal to 1, right. So, these are the combinations. Now, we will write the truth table. Okay. Whatever we have checked like this thing you can write the truth table like that, A, B, C, D, E, F, G, total 7 segments, and to display 0 we have to check this, for display 7 we have to check like this, for displaying 5 like this, like that you have to write the truth table for 0 to 9, right. Now, from the truth table we will do the K map and we will solve the Boolean expression. So, now let us start from the first one, this is for 0. So, for 0 again one more thing, here you can check, see only we are having 7, 0 to 7, 1, 2, 3, 4, 5, 6, 7, right. What about the rest case? Rest case means from 9, only 0 to 9 we can display, right. This is from 0 to 9, but what about 10, 11, 12, 13 and 14. So, these will be the do not care conditions, right. So, for like that only here in the truth table you can check, this is 0th position 1, 3, 2, 4, 5, 7 and 6, and rest we are having cross. Okay. So, like that for A, to display A, this is the truth table for A. If we write the truth table for this full, okay, so we will be having this will be the truth table, okay, and the value will be capital A plus C plus B D plus B bar D bar. Like that, if we make a K map for this B, I have not written the full truth table, you can complete by yourself itself, okay, and this will be up to 9, 0 to 9 this truth table will be there, up to from 10 to 15, okay, that will be all cross. Okay. Next, so for displaying B, so we will be having B bar plus C bar D bar plus C D, then for C we will be having B plus C bar plus D. Here we are not nothing but making the truth table for this, okay, clear. Okay. Now, we can check, ultimately these are the final equations. So, for A we will be having A plus C plus B D plus B bar D bar, for B we will be having B bar plus C bar D bar plus C D, for C we will be having B plus C bar plus D, for D we will be having B bar D bar plus C D bar plus B C bar D plus B bar C plus A, for E will be having B bar D bar plus C D bar, and for F we will be having A plus C bar D bar plus B C bar plus B D bar, and for G we will be having A plus B C bar plus B bar C plus C D bar. So, total how many K maps we have to make? A, B, C, D, E, F, G, total 7 K maps we have to make, and from the 7 K maps we will be giving this minimized expression for A, B, C, D, E, F, G. Okay. Now, if we going to implement the circuit, this is nothing but the circuit diagram, whatever we have done the equation we have just implemented it like this. Okay. So, this is the complete circuit diagram for 7 segment display. Next. Okay. Now, 7 segment display is over. Now, we will be going to discuss about parallel adder. Okay. So, adder already we have discussed, full adder, half adder we have already discussed. Now, parallel adder. Okay. So, parallel adder will just give an example of normal decimal number. So, suppose we are going to add 4, 3, 2, 1 and 1, 2, 3, 4. So, like that. So, 4 plus 1 5, right. If just check one thing, we will give some other value, we will give here suppose 9 8. Okay. So, 4 plus 1 5, any carry? No. Then 9 plus 2 11. So, it will be 1 and carry will be going to there. Okay. Now, 3 plus 8 11, 11 plus 1 12 and carry will be 1. So, 4 plus 1 5 plus 6. So, see it for each addition, if there is a carry, it is going to move further, right. So, same concept we are going to use in binary addition also for parallel adder. Okay. Let us check. So, adders are nothing but the combination circuit which are used to add two binary numbers. Already these example we have studied, full adder and half adder. The nature of adder chosen depend on the characteristic of the binary numbers which need to be added. Which type of addition we are going to do, by that we will choose the adder, right. If we are having 2 bits, then we will be having half adder. If we are having 3 bits, we will be having full adder. If we want to want 4 bit and more, then we will be having parallel adder. Okay. So, here it is written that why, if we are giving 2 bits, then we will be having half adder. For 2 bits, half adder is enough, right. So, if any additional bit is there, then we will use full adder because it is a 3 bit addition. And if we want to add a binary number which has multiple bit in it, in such case we need the parallel adder. Okay. So, whatever I have given the example for decimal number system, same thing will be depicting here as A2, A3, A2, A1, A0, B3, B2, B1, B0. This is nothing but the binary case we are going to implement. So, here we are taken a number as A3, A2, A1, A0. This will be A3, A2, A1, A0 could be like this 1 1 0 1, okay, and B3, B2, B1 and B0, that will be 1 0 0 1, like that we can take. So, first of all we will be adding A0 and B0, and here we have written seen as 0. So, at the beginning there is no carry is there. So, C will be 0, right. So, addition of A0 and B0, sum will be S0. Okay. If any carry is there, if is carry is there, it will be moved to further. Okay. In second case, we will be adding A1 and B1 and this carry from the previous stage will be added and we will be forming S1. Again the carry 1 C1 will be moved to the next step, and A2 B2 when I am going to add A2 and B2, C1 will be added to this and it will be giving the result as S2. The C2 whatever we are getting, it will be moved in the next step and it will be added to A3 and B3 and it will be resulting S3 and C3 will be moved further. Okay. So, like that if we check from here, so 1 1 binary addition rules, 1 1 sum 0 carry 1. So, sum will be 0 and carry will be 1. So, carry will be 1. Next 1 plus 0 plus 0, that will be 1. Any carry? No. So, it will be 0, 0 carry. 0 plus 1 plus 0, 1. Any carry? No. So, 0 plus 1 plus 1, again sum 0 carry 1. So, it will be sum 0 and carry 1. So, this will be the final output. Okay. So, this is the logic behind the parallel addition. Now, we have to implement a circuit which is going to show the output as parallel adder. Okay. So, let us check this is the logic diagram. So, in every case, see one more thing, in every case we are adding 3 bits A naught, B naught and Cn, though it is Cn is 0, but we have a provision of adding C naught Cn. So, when we are having 3 bits we are using full adder, right. So, the block diagram of parallel adder is nothing but the combination of 4 a more number of full adders. Here 4 bit addition is there. So, we will be needing 4 full adder. Okay. So, Cn A naught B naught. So, 3 bits. So, 1 full adder will be there. So, you can check 1 full adder, we are having B naught A naught as input and Cn is also input, okay, though it is 0, but we have to the provision of adding it. So, it will be giving as output as S naught and the carry C naught will be moved to the next full adder. Here the inputs are B1 and A1 and combination of 3, addition of all 3 C naught, A1 and B1 will be giving the output as S1. Again carry C1 will be the carry, it will be going to the next full adder. Here the inputs are B2, A2. So, it will be added with B2 and A2 and will be giving the output sum as S2. The what about the carry? Carry C2 will be going to the next full adder. Okay. So, here the inputs are B3 and A3. So, it will be added with B3 A3 will be added to C2 because it is a full adder, addition of 3 bits. So, it will be giving rise of S3 as output sum and C3 will be the output final carry. So, the finally output will be C3 S3 S2 S1 S naught. This is the final result of parallel adding. Is it clear to you? So, this logic diagram is made of full adder because full adder is used to add 3 bits. Okay. So, if we are want to use a single IC for parallel adder. So, this is the pictorial representation of a single IC for 4 bit parallel adding. Okay. Here these are the addend B3, B2, B1 and B naught. What is addend? Already we have discussed here, addend and augend. Okay. So, here B3, B2, B1, B naught, one combination of 4 bits and augend is A3, A2, A1 and A naught. These are all coming to a 4 bit parallel adder. Here Cn is 0, this is a single IC. So, the output is S3, S2, S1, S naught and the final carry is C out, right. You can write as C3 also. So, like that we will be getting output as C3, S3, S2, S1 and S naught. Here in the previous diagram we are using separate full adder and this diagram is nothing but a combination of all full adder and this IC number is nothing but 7483. This 7483 having the provision of 4 full adders. See, it is written like that. See, we are giving A naught and B naught, we are having like that, we are having, sorry, here 1, 3, 4, okay. So, this is A1 is pin number 10, B1 is pin number 11, like that A3 is pin number 3, B3 is pin number 4 and some 3 will be from pin number 2. Okay. So, like that the IC has been fabricated, designed. So, and this is the IC number of 4 bit parallel adder. Now, next was the list, we are having CL adder. So, till now we are having addition of parallelly, we are doing the addition parallelly. Now, one by one, CL is nothing but 1 by 1. So, here these are the CL inputs, we can write that this is augend, this is addend. Same like the previous one, now we are be going to add serially. So, here we can write as A3, A2, A1, A naught, this is B3, B2, B1 and B naught. You can add multiple number of bits. Here we are taking 4 bits A3, A2, A1 and A0, B3, B2, B1 and B0. Okay. So, now here again we are using a full adder. So, the first is input as A, which is coming from A3, A2, A1, A0, this is B, and the sum will be here. So, the sum will be S3, S2, S1 and S0. For each addition case, first these two will be entering A0 and B0. Okay. A0 and B0, the sum will be S0, sum will be S0 and the carry C0 will be stored in a memory. Okay. And this C0 will be used when the next set of bits A1 and B1 is added. So, you can say first of all A0 and B0 will be entering in the full adder circuit and generate S0, and C0 will be coming out and it will be stored in the memory element. It will be used when, it will be used in the next case when A1 and B1 enters the full adder circuit and generate S1. Okay. Then C1 will be again stored in the memory and will be used when we are going to add A2 and B2. It will generate S2 and our carry will be C2. This C2 will be stored in memory element and this C2 will be used further when we will be going to add A3 and B3. So, you can check one thing, that here we are using the concept of memory, we are using concept of memory, but normally combination circuit does not have memory, right. So, though parallel adder is a combinational circuit, but serial adder can be considered as a sequential circuit, because here the concept of memory is being used and whatever we are getting the carry will be stored in the memory and it is being utilized in the further addition process. Okay. So, our parallel adder is a combination circuit, but serial adder is the sequential circuit. Okay. So, let us check the comparison of parallel adder and serial adder. So, the first comparison is serial adder, parallel adder is fast because all numbers is added simultaneously, but serial adder is slow because one by one. You can check in the first diagram, first A0 and B0 will go, it will be adding, S0 will be getting, again will be A1 and B1. So, one step is completed, then the next step of addition is started. So, for that reason serial adder is slow. More requirements are required in parallel adder, more number of equipments are needed, less equipment is needed, because you can see from the diagram itself, in the parallel adder we are having 4 parallel adder, 4 full adders, but here only one full adder is needed, right. So, that is the next difference, that n number of full adder circuit is needed and here only single full adder is needed, single full adder is needed. Okay. And again I have told that for parallel adder it is a combination circuit, but serial adder we are having the concept of memory. You can check it back, here we are using memory, because whenever A0 and B0 is added, S0 is stored in the serial output, but the C0 will be stored in memory and it will be added to A1 and B1, right. So, here memory concept is used. So, for that reason serial adder is sequential circuit. So, the last difference is, it is an example of combinational circuit, whereas serial adder is nothing but sequential circuit. Okay. So, we have discussed all the things. First of all, we have discussed the 7 segment display, okay, and then we have discussed parallel adder. The concept of parallel is very simple. Here 4 full adders we are using for addition of 4 bits, number of n number of full adders can be implemented when you are going to add n number of bits. Okay. And we have discussed about the IC number of full parallel adder, that is 7483, and next lastly we have discussed about serial adder, and the most important feature of serial adder is it is nothing but a sequential circuit. Okay. So, thank you.